So welcome to lecture 6. In lecture 5, we left off with the idea that Euclidean geometry start with some basic definitions of point and line and so on, and then it assumes few axioms and some postulates, and from there Euclid tried to construct the whole geometry out of it. Right? Now, what I was saying in the last video, and we will discuss in a few minutes here, that Euclidean geometry does not only assume those definitions, axioms and postulate. Those are different set of assumptions. We put that in one box. Those definitions, axioms and postulates are about objects, geometrical objects. So we put that into one box. Those box has to do with space, Euclidean space. Euclidean space, for now, since we are working in 2D, we can say two-dimensional plane. For example, chalkboard. A chalkboard is a two-dimensional Euclidean space. Or you can say the notebook, the paper. A notebook, the plane of a notebook is a two-dimensional Euclidean space. So those axioms, definitions and postulates that we find in book 1 of Euclidean geometry, those are about Euclidean space and the object that sits on those objects. So we put it into one box, those definitions, axioms and postulate. Now, Euclidean geometry also assume one more thing, but it doesn't. But those are unspoken facts. Euclid never assert that this is what I am going to assume. He is working under a frame of a logic, and he doesn't say in the book that okay, so this is what we are doing assumptions. It is understood. He doesn't have to say that. He just he has to say that. He had to say it, but he didn't. And what is that assumption? The assumption is the kind of logic you assume to construct your geometry. Those axioms are fine of the geometrical object. What is point? A point is something that has no part. A line can extend up to infinity in both directions, right? Or given a line and a point, there exists exactly one line that will be parallel to the given line. Given a point, infinite line can pass through it. These are the assumptions. That is fine. You keep it into one box. But those assumptions only work because you assume one more thing, and that is the nature of logic. What kind of logic you are working in? And those logic is binary logic. Euclidean geometry is based on binary logic. Last time we saw that all those statements of Euclidean geometry can be answered in yes/no question or true/false, 1-0. If we have two lines given on a plane, either they intersect or they don't. It is either true or false, right? Given a point and a line, those point either belongs to the line or it does not, true or false. So now we are trying to see what is happening here, right? We are trying to see the logic that is built into the Euclidean geometry, and we will see in detail. So let's begin on the paper. So here we are going to see assumption in Euclidean geometry. Assumption in Euclidean geometry, right? We have two sets of assumptions. First is about geometrical fact. These are into one group, and these can be, for example, a statement like point has no parts. Given a point and a line, there is actually one straight line passing through it such that it is parallel. Given a point, there infinite line can pass through it. A line is something that is made up of infinite points, and so on. These are the geometrical axioms, and we are not questioning this. axioms are not questionable, right? These are the assumptions. Now, there is another fact that Euclid does not say in his book, and that is itself, the assumption is logic. What kind of logic we are working in? Euclidean geometry works under classical logic. Classical logic means binary logic. Binary logic means given a proposition, we know what a proposition is. Given a proposition or a statement, it can be either true, which is 1, or false, which is 0. We can assert this number, we can assign this number to any kind of propositions in Euclidean geometry, right? For example, either true to a straight line meet or do not meet. It is either true or false. Another example could be either a point lies on a line or it does not. This is also true or false. See, so the logic is here binary. Every statement can be true or false, right? So now this is not the case with only Euclidean geometry, right? Euclidean geometry, we just took it for example. This is the case with whole foundation of mathematics. Whole classical mathematics is built on classical logic. Classical logic means where the truth value are only two truth value, either 1 or 0, true or false. Every mathematical statement we can assign these two number, true or false, 1 or 0. And whole classical mathematics, either it is algebra, set, topology, anything, everything is based on these two idea, 1 or 0, true or false. It is binary, right? Now, let's consider this statement for a second. This one. Either a point lies on a line or it does not. And let's try to see how classical logic is functioning in this. And we have to see it very clearly so that we can have an idea that how does it work. Okay. So what does it say? The statement is, given a point P and a line L on plane, the line is on the plane, and given a point and a line on a plane, either P lies on the line L or it does not. What it is trying to say? Now first we have to assume plane, because every mathematical geometrical object lies on the plane. Since we are talking about 2 dimensions, we are going to talk about 2-dimensional plane, 2-dimensional space, Euclidean space. What is a plane? Plane is take a real line, and then the same real line and do the Cartesian product with itself. This is a plane. Now we are not going to talk about what is real line. We are going to assume that we know what a real line is. That is 0, 1, 2, 3, minus 1, minus 2, minus 3. Here is 0.5. Here will be somewhere root 2, right? Here will be somewhere pi, and so on. So we know this is a real line. Now the notation for real line is this, R. So what is a plane? Plane is take a real line and do the Cartesian product with itself, which is R square, right? What is the Cartesian product? Well, I don't want to say this right now, but we can say Cartesian product is take a number from this set, this real line, and take a number from this real line and put it in order. Right? Let's say from this we took a point, a number A, and from here we got a number B, and we put it in a comma and it become a pair. We cannot change it. We cannot write b comma a because they are different things. So this is a comma b, right? So this is Cartesian product. This is how we evaluate Cartesian product, taking a point, taking a number from each set and put it into a bracket, and it becomes an ordered pair. Now we'll talk about this in detail later. Now so this, we have a plane r square. Given a plane, it says there is a line on the plane. What does it mean, line on the plane? So here is a plane. So this plane, you can imagine this plane as this plane has point everywhere. Like here at this location, we can assign a number, this kind of number, a comma b. For example, here also we can assign a number a1 comma b1. These are the location, and we can do it for the whole plane, right? The whole plane has this kind of locations. We can talk about location of each point. For example, here, what is this one? This is a location in this plane. So we can assign a number a comma b, right? A2 comma b2, let's say, because a comma b we have already used here. So in this way, the plane has infinite points, and we can assign point to each location. Here. There are so many. Everywhere there is a point, right? Now, if this is the plane and the line sits on the plane, so here is a line. It means this line must go through the points of the plane. If it is on the plane, there must be these points through which this line is going. Those points already belong on this plane, on this paper. So what is line then? Line is just collection of point, a collinear point, like sitting on the same, boundary. But these points are not just the points, all the points of this plane. What about this point? What about this one? What about all the point which is here? This is just a small set of point of the plane. Plane has so many points here. Line only talking about, this line is only talking about this kind of point. And these points also sit on the plane. It means this line is nothing but a subset of this plane, right? A small set of this plane. So we can write, given a r square, and let's say L is subset. This is the notation for subset. So this line is subset of this plane. Okay. Subset means this r square is a very large number of points. Here is the r square, this plane, this paper, and line is just a small boundary on the plane. So it is not a bigger set. The bigger set is this one. This one is lying on this, so it must be smaller than this whole thing. That's why L is subset. It is subset of r square. Now what is a point? A point here, let's say we're talking about this point. So this point is the element of this line. Element, not subset. This is element of this line. For example, this point either belongs to this line or it does not belongs to this line. So we can say point is, this is symbol of belongs to. It means lies. Let's say for us now, this belongs to symbol means this point lies on the line, right? Or point does not lie on the line. This is a symbol for does not lie. Or you can say does not belongs. So here is a point. This point does not belong on this line, but this point belongs on this line. It lies on this line. So given a plane, we need plane to work geometry. So given a plane and a line which is subset of this plane, then either this point P is the element of this line, it lies on the line, or it does not lie on the line. So this is what this statement is trying to say. given a line and a point, either this point P lies on this line or it does not, true or false. And we wrote it, we can write this statement in mathematical form like this. Now we can write it more in a general way, more mathematically in logical form, which is this way, and you don't have to understand it. Just it's a simple but we will not. We'll talk about this later when we will study logic. So what did it say? Let's say this is the plane. On the plane, we don't have only one line. We can have infinite line on here. We can draw here. So many lines we can draw, right? So for these all lines, for all symbol is this one. This is for all. It means for all these lines, that is for all these lines. So we write this for all these lines. For all these lines, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, there could be infinite number of lines here. So for all these lines, but the all line is a subset of R square. Here we see that. All line is subset of plane. It lies on the plane. So for all line, that is subset of R square. And also for all point, that belongs to the line. So take a line here. Either this point belong here or it does not belong here. So, sorry, I made a mistake here. I'm sorry. This will be R square, because a plane is set of point. So here are point everywhere on this plane. These are the point on the plane. So these are the point. If I draw a line like this, so see, this point didn't lie on here. This point also didn't lie on this line, right? But this point does lie on this line. So all these points belongs to this R square, right? So we can write here, point belongs to R square, but line is subset of R square. So for all line, that is subset of the plane, and for all point that belongs to R square, that is element of R square, then either this point belongs to this line, or this is the symbol of or, and this means same thing that we mean or by in English, or this P does not lie on this line. So this is our statement. So this statement is clearly the same statement here. Let's write it here clearly. Our statement was, given a line and a point, this point either belongs to the line or it does not. So given any line, for all line, we're not talking about just one line, for all kind of line that is subset of our plane, it means lies on the plane, and for all point that belongs to, that is element of our plane, two things happen. Either this point lies on this line or this P does not lie on the line, right? Now, what does P does not lie on the line means? P does not lie on the line means P lies on the line and we negate this statement. It means this negation means this P belongs to L. This means P lies on the line, and this not, we are putting not symbol here. This is the symbol of not. It means P, no point lies on the line. So these statement and these statement are true. Same thing. P does not lie on the line, P lie on the line, and then put not here. It means P does not lie on the line, right? So it means we can write this as P lies on the line or no P lie on the line. Or more generally we can write P, or this is about line. We can throw this line away. It can be anything. So P or not P. What is this? This is law of excluded middle. And next lecture we will continue from here. What does it mean?